Good morning. It's a pleasure to be back in Cetraro and have this opportunity to talk about smart and photosensitive materials. And I will be building up on the concepts that were introduced by Gaetano and Marina, both in terms of liquid crystals and photosensitive materials. But I also would like to, and I'm glad that the theme of that session is going beyond just fascinating demonstration of new effects, but also showing applications. So going that next step towards innovation and where those effects and materials can be used in the future, because I think that's where, interest is. So I would like to introduce the rest of the team, and so you will see the results from colleagues, both from my groups of photonic system group in Southampton, working with some chemists, also colleagues from mathematics in Southampton. The work on photovoltaics is a joint collaboration with Thomas Heiser group from Strasbourg, and we also have collaboration with our colleagues from Warsaw. So let me move on. And so as I was saying, one of the, when we, explore new materials or new designs or new geometries, I think especially in the soft and organic optoelectronics area, it's useful to remind ourselves where the field is going, because I think in particular for liquid crystals, this is a mature technology. And therefore the expectation is that when you are exploring a new effect, you are doping, merging with other organic or inorganic layers, there is an expectation that you know what the state of the technology is. So I listed here some, I think, the trends which I believe are on the move up, and that of course includes in terms of display, perhaps less so the standard displays, but going, for example, from retina displays, but also very wide area. How do we actually make those technologies more efficient and cheaper? And of course, augmented and virtual reality. This is, I think, a big field for expansion for liquid crystals. In terms of components, I think the liquid crystal lenses, whether that would be the contact lenses or lenses that are adaptive, I think that's where the fluid nature and the birefringence of liquid crystals, I think is very promising and I think something to look at. Now, optical components, yes, the spatial light modulators, are based on liquid crystals. However, it's actually difficult to compete in the visible and near-infrared regime with what already exists. So I think the last few years there has been a lot of focus on the areas of the spectrum where the components are still lacking, and what you have here, I guess Terra has one equally, mid-infrared is still a challenge. So in terms of actual, devices, I think with the kind of more energy agenda, more prominent, how do we make smart windows? How our actual devices are more energy efficient? So that's, I think, where the angle is, where we can explore and use sort of new materials. But also, I think, two other examples, and I will show you, I think, one that we got interested in, the biological and self-assembled liquid crystal systems. The systems that are structured and therefore more resistant to antibiotics because they are structured. But also, I think one of the areas that I think is still very vibrant is putting those different nanoparticles, nanowires, active, passive, in liquid crystals because they are such a fantastic host and new functionalities and structures. So as I said, fascinating science is behind it, but I think, fascinating science quite often is not enough to actually push your ideas forward. So I would like to split my talk into kind of two parts, or there will be two themes. So, well, I will be talking about the fabrication of liquid crystal systems. I would like to focus on this. So, yes, you have your new system. How can you understand what's happening? And the more complex the system is, of course, quite often fabrication is the easy part. The modeling is the hard part. But this is the theme is here, the smart and kind of responsive active materials. So I would like to start with something we, in the standard characterization techniques, moving towards photosensitive photovoltaic system, colloidal systems, and then how do you actually characterize those? So let me start with a very simple cartoon. How you actually build up your devices. And on the left, you see, a standard sort of very simple graph where you have, if you are looking at the liquid crystal cell, you have a top one and a bottom one, which is an ITO with some passive aligning layer. Then you have a liquid crystal in the middle. In this case, is aligned as a planar alignment. But then what you can do, and that has been done, when you actually take this top slide, for example, and you try to build some structure in this. And a typical one is, the azobenzene layers that Marina was talking about, and other photo-aligning layers that you can actually align that surface instead of mechanically rubbing it. You can address it with light, and you can use this to manipulate liquid crystals. You can also, and I will be showing you, build a photovoltaic cell effectively on that second substrate. And again, you can control the whole device with light, electric field, or both. The third one I will not be actually touching on, but I wanted for completeness. You can also structure your substrate, and this is an example of the work we've done a couple of years ago when it is a material structure. You have a resonance structure that you can actually work as a polarizer and an electrode, and also has a resonant response. But while you are playing with this in the lab, I think the more options you have, the quicker you realize that you need something robust to characterize it. Because, whether you're using a photolining material, you may have a few of them, they may age, they could behave differently depending on the moisture in the lab. There are many parameters that, you are trying to work out what's the best optimized device. So one of the standard techniques to actually see how your liquid crystal cell, whether it's passive or active, is to look at cross-polarized intensity measurements, where you see in the middle, you see your liquid crystal cell, and this is, you have a laser, you have some initial polarization set by the first polarizer, your liquid crystal cell, which is effectively like voltage controlled wave plate, and then you have your analyzer, and then you collect your signal connected to a oscilloscope. You can see how the intensity of your signal changes as you apply the voltage. And that curve is so rich in information. It contains, the parameters of your system, your cell thickness, the birefringence, depending on the wavelength. So it's actually, there's a lot of hidden in that curve. And that's what we actually looked, and I will not touch on this, but what we've developed, because, as I said, playing with nanoparticles, adding photovoltaic with a sensitive layer, what we spend a lot of time is trying to decode that curve to provide us with some very important constants and parameters of the system. And this is actually important for us, that you do not look at a single parameter of a single layer, you look at the performance of the whole thing, integrated device. And there are some key parameters like elastic constants that really determines how your liquid crystal responds to external stimuli. Viscosity, which is related to response time. Optical quality, that they actually change with time, and sometimes they do. The thickness and the birefringence, and how strongly your liquid crystal is anchored on your surfaces, especially as you are, changing those surfaces by using different materials. And also, how thin you can make your device, which is important for, as I said, for the augmented or virtual reality applications, and so on. So I think that was, for us, an important step in understanding what we are doing and helping us with optimization of devices. So this is our optical analyzer that I will be showing you some results from, and that's what it looks like. So you can see the interface, and on the left, this is a standard passive planar cell with 5 CB, so we can get the cell thickness, pre-tilt, and anchoring energy. And we have just completed the second stage of the project, where we look at the other elastic constant, K2, which is important for the twist cells. This is the most common configuration when you're looking at displays. So these are the measuring the elastic constant, and I will not talk here about the viscosity. Let me just do how I'm doing for time. Okay. So we published this recently. So let me move on to those active systems, and this is something. 12 minutes. So what I would like to show you, so we have talked so far about the standard systems with passive layers, but what we did is use the azobenzene that Marina was talking about as a thin layer on one of the substrates, and we looked at configuration of the 3 cells. So A is just a standard cell with polyimide wrapped with E7. In the middle, we are exploring, different types of electrodes, and they're also wrapped P.PSS with a different liquid crystal that has a very low threshold. And on the right, you see the cell, the C design, where you use this photo alignment layer, that we use this concept of using light polarization to align liquid crystal. And I just want to show you what we can get from very quickly from our analysis is a snapshot how these cells perform, how they age, and what we were interested in particular, what was the anchoring of liquid crystals on those sort of novel, I think different, more active surfaces. And as you can see in the table below, you can see that on the standard PI, the anchoring is quite high. And then when we move to P dot and pad, the anchoring actually decreases. And the middle cell, our cell B, is important because we are using those layers and those liquid crystals in our photovoltaic systems. So I think this was kind of in preparation for the kind of self-powered system, but I'm sort of showing it here that it's kind of step-by-step methodology when you try to understand the basic kind of performance of those devices first. And as you can see, you can look at how the thickness and the pre-tilt changes across the liquid crystal cell. So let me move on to photovoltaic modulators, because I think this is one of the most exciting developments where you actually combine 2 technologies together. You have your photovoltaic cells and you have your liquid crystal technology. And of course, in terms of photovoltaics, the organic electronics is the gold standard and have to kind of compete with silicon. But it's also important to note that we are looking at organic semiconductors that can be cheaper, that you can cover a large area. Of course, you want something that is efficient, but also something that can integrate like we've just done with azobenzene, with other organic layers. And I think this is one of the strengths of the organic semiconductors, this ability to actually construct, almost like Lego-like, your surfaces and your devices. So what I would like to show you is a basic concept of the device. So what you see here is the middle part where you see the blue arrow. It's basically almost like a usual solar cell without a top electrode, very briefly. But so in more detail, what you have is you have your two polarizers and polarizer and analyzer at the top. Then when you look at the going from the top, you have ITO glass with an aligning layer, so nothing special here. But then the bottom part, you again have the ITO glass and your sort of solar cell structure. So you have your hole transporting layer, you have electrons transporting layer, and this bulk heterojunction in the middle. So this is a transparent layer. So what you are getting is, you have your light kind of incident on the structure. What the role of the system is that, your bulk heterojunction layer absorbs those photons, generates those charges, and they go to the hole and an electrons transporting layer, respectively. But the transparent organic layer is also serving as a sort of alignment layer. So you try also to minimize the number of layers you want to add in this device. So in the typical off state, you still have your light generated, your charges got separated, and depending how efficient your solar cell is, you can see that there is some photovoltage generated. And until you actually connect top with bottom, actually nothing happens. It's still, light goes through and so on. This is a twisted cell, so light goes from the bottom, gets twisted, and then it goes through the other cross polarizer. So nothing happens in the off state, and you can see on the right at the top the photo of the device. Now, what happens when you then connect those two wires, you have your photovoltage drop across the liquid crystal. And some of these liquid crystals that we work with, they do not require, a high photovoltage. There are liquid crystals that, have a voltage threshold around 1 volt or slightly below. So it's not that you need to generate a huge amount of photovoltage, but which means that you could actually, just by using light alone of sufficient intensity, because of course the photovoltage would depend on light intensity, you can actually switch the liquid crystal on and off, like you would do by applying just external electric field. Or you could use both photovoltage and electric field if your photovoltage is not strong enough. So in this case, you get a dark state. And so these are the kind of examples of on and off. How much time do I have? Sorry. How much?
10 minutes.
10 minutes, okay, so I don't need to rush. Okay, so these are just, some examples of the PSLN cells. As you can see, one of the issues is actually make them, absorb in the visible and yet make them, sufficiently, transparent. But these are just sort of examples that I'm showing you just for demonstration. So what we've done, as I said, I'm going back to the role of characterization, because here we have probably one of the most complex structures we investigated so far. And yet, as I said, we wanted to see the performance and the response of the whole device. So we've kind of adapted our analyzer to actually being able to extract some parameters of this sort of photovoltaic system, in particular the photovoltage. So as you can see, what we've given an example of one of those many versions of these photovoltaic cells is that you do have actually, by using, you have 4 examples of different, light intensities here, and you can actually extract the photovoltage that you achieve at each of those intensities. And for comparison, you can actually measure that independently. Now, the main benefit of that is of course, each device that you fabricate, yes, you can take out, you can use your solar simulator to extract the photovoltage. But I think what we are interested in, how you can actually speed up that process a little bit, how you can actually at the same time look at the performance of your device in terms of optical quality, because that is still a concern. You still have, a complex structure inside your liquid crystal. How uniform is your device, especially if you want to achieve, large area, and how it actually potentially degrades over time. So that's where, we are going forward. Now, the results I'm showing you right now are small in terms of photovoltage. We just achieved sort of self-powered action, but the results are not yet ready. We're preparing a paper on this one. So, but as I was saying, this is a potential and route for, again, energy efficient, smart devices, which are driven not just by kind of electricity and your power generator, but by light, including sunlight. So what are the challenges? Okay, of course, we want to have photovoltage that is stable, that is large enough to achieve smart operation, sort of self-powered system. That requires the optimization, what liquid crystal we want to use. That includes, the voltage threshold, but also how dielectric or how conductive your liquid crystal is. And that's a concern, because I think the liquid crystals quite often may have different conductivity when you freshly open a bottle. And then, if you keep using the same bottle, you would introduce impurities. So I think there are a lot of kind of practicalities that can affect the performance of your device. And of course, liquid crystal alignment is an important one. How well you can actually, with all that structure, generating that photovoltage, how you actually make sure that you can also align your liquid crystal. Of course, we want devices to be robust with long-term stability. But also, this is a concern when you're thinking about technology. We still need clean room, okay? We still need specialized equipment. It's not something that you can put together quickly in the lab. Maybe at some point, but not yet. So I just want to touch on the last aspect, is on colloidal liquid crystals. Because I think in our drive to look at how we can play with liquid crystals, we came back to the idea whether you can add nanoparticles to reduce voltage threshold. This is difficult, but I think in terms of the potential impurities that you're introducing at the same time, but I think that brought us back a little bit to the idea of actually looking at active nanoparticles in liquid crystals. So what we explored are actually nanoparticles, very small, 2 and 4 nanometers. They have those azobenzene ligands that Marina was mentioning as a theme. And basically you add this to, let's say, a standard liquid crystals. And there was some really nice paper from Oleg Lavrentovich's group a few years ago, how you can actually use light to align those cells. So let me show you what we've done. We created those cells. I'll show you for what application in a second. But again, as you can see, even if your nanoparticles are small, the concentration is low, you can actually explore the effect and characterize your cells in terms of anchoring energy, pre-tilt thickness, and so on. Thickness is actually something that is very helpful, as you are learning how to make cells, whether you can actually, make uniform cells. So it's actually, a useful kind of fabrication feedback on how well, if one is producing cells, can make the cells uniform. So what we did, we of course ran our sort of typical characterization mentioned before, and as you can see, we can capture both for E7, of course, for reference, and our gold nanoparticles as a benzene. We can look at how the elastic constants are affected. We look at the pre-tilt, the anchoring, viscosity, and so on. The details of that work is in Nicholas' paper from our group, published earlier this year. And I think there was an interesting exercise in trying, okay, as usual, you get your result, you compare it with the unlocked system, and you say, okay, it's decreasing. You compare it with published sources, and in some cases it is shown, other groups shown that it's increasing, in some cases are decreasing. And then you dig a little bit deeper, and it's actually, providing useful information whether your nanoparticles are aggregating or not. So again, a useful tool for your fabrication and for understanding what happens with your systems when they are already in a cell. But this was actually just a small preparation to the project we had in mind, is that, so what happens if you're really loading your nanoparticles? How many minutes? 2 minutes, okay. So what you see here is the nanoparticles before, they were sitting happily somewhere around your host, but here we are loading this liquid crystal host, and they are forming networks. They are talking to each other, and like we at the conference, we are networking. They are networking with each other. You can put them in confined geometries, and therefore you cannot treat your system as, here's a liquid crystal with a weak perturbation. And that's what we tackled in our recent project, and this is the paper that just came out earlier this year. What happens is that we're looking at the new method called topological data analysis to analyze those systems, which are actually very difficult to tackle in any other way. And this actually stemmed from some very nice work from Hiraoka, where he used it for amorphous solids, for glasses and polymers, first theoretically. Also, the work from our colleagues from mathematics for lungs. So what we are using in our soft matter is that new method where you look for hidden patterns, you look for spatial arrangements that are not that obvious, and you attach numerical descriptor. So it's not only you're maybe doing some Fourier analysis, you really try to quantify and detect structural changes. And of course, that leads, once you detect it, what does it mean? How it actually links to the function of your system. So what we've done is, and these are a number of examples where you actually, soft matter is a rich field for such complex matter, whether these are the defects in liquid crystals, biological systems, complex structures, cellulose. There are plenty of examples where you do have this not perfectly ordered matter, and yet, apart from trying to do it, very simple analysis, there's actually very difficult to try to model, understand, and see what structure they have. So I will just, this is my last slide, so I'll skip the details. I will have one slide where I explain what the method was. But what we did here, as you can see, this is our azoxyl nanoparticles. We load them in E7, and you can see how these structures and networks form. You can kind of play with them with temperature and electric field. And you can see that by changing the cooling or heating rate, you can actually create longer and shorter networks. And that means that, you know, you can have networks, in some cases you have clusters. So normally it will not be possible to tackle and analyze these. And this is test bed. It's not that we want to, you know, make, you know, a particular device. It's, you know, testing our method on networks that we can control. And these are sort of our results just from last month, where you look at the average size between disconnected components and the cooling rate. So I will not have time for this slide, but let me just jump to conclusions. And I just wanted to show you in my talk that liquid crystals with photosensitive or other active layers is a really fantastic way to explore and combine the really promising prospects of those organic electronic systems. And what we are looking in particular is sort of self-powered operation, energy efficient components, and underpinning is our characterization and optimization. The optical method, fantastic for a straightforward system. For more complex system, you know, more ambitious, we need to use topological methods. And of course, there may be other methods where you have structured matter, where you have self-assembly or semi-ordered soft matter. And this is the paper I mentioned earlier. Thank you very much.